Welcome to our deep dive today. We're going to be taking a look at personalized intelligences.
Okay.
It's a paper by Jerry Allen Fales and Dan R. Olsen Jr.
Sounds good.
And they're looking at this problem of perceptual user interfaces, or PUIs, as they call them.
Right.
And so I guess kind of the idea there is, like how can we use things like gestures and voice control to make our devices
Yeah.
more intuitive.
More human, right.
Yeah.
Exactly.
Exactly. And, one of the biggest challenges they point out is that it's actually really hard to build these accurate image classifiers.
Yeah, and that's really a huge barrier to wider adoption. I mean, especially for,
Yeah.
UI designers, they don't always have that deep machine learning background.
Right.
To build those classifiers is really time consuming. That's
Yeah.
complex.
Exactly. And so this paper is really kind of diving into a potential solution to that.
Right.
And they call it interactive machine learning,
Yeah.
or IML.
Interactive machine learning.
Yeah. So what's the goal here? What are they trying to achieve with this?
I think the big goal is to make it a lot easier and faster for designers to create these classifiers.
Okay.
Streamline that whole process.
So to get started, they kind of contrast IML with classical machine learning,
Right, which they call CML.
CML.
Yeah.
So what are the big differences there?
So in CML, you've got these distinct phases. First you do feature selection, then you do training, and then finally you get to classification.
Uh-huh.
And it's really optimized for that classification speed. But that training process, man, it can be really slow.
An IML kind of throws all that out the window, right?
Yeah, IML, it's all about the loop. Feature selection, training, classification, it all happens concurrently.
Okay.
And the user is constantly giving feedback. So as you're interacting with the system, it's learning and adapting in real time.
So it's constantly kind of like retraining itself based on new input.
Exactly.
Okay. So they introduced this tool called Crayons to kind of illustrate how this works.
Right, Crayons.
And from what I gather, it's designed to have a pretty simple process. You input some images, you create the classifier, and then you can export it to use in your PUI. Pretty straightforward. But then they go a step further, and they actually show us the architecture behind Crayons.
Right.
And it's really all about this tight feedback loop.
Yeah.
So can you walk us through that loop a little bit?
Sure. So you start by inputting an image, right? Then you classify it manually. The system creates a classifier based on that, shows you some feedback, you can correct it or refine it, and then finally you export that trained classifier.
So it's really like this iterative process of you working with the system to get to the point where you have something that's accurate.
Exactly.
Okay. And they give this, they actually give an example of using crayons to build a skin classifier.
Yeah, that's a really cool example.
And it shows how quickly you can actually get to a working classifier with just a few rounds of, input and feedback.
A few iterations. You
Yeah.
get there pretty quick.
Yeah. So now we kind of get to the heart of this.
Right.
You have this interactive environment.
Mhm.
You need a machine learning algorithm that can kind of keep up with that.
Right, right. And IML, it's got some pretty demanding requirements.
Okay. Such as?
Well, for one, the algorithm has to be super fast at training. It's got to be able to handle, potentially thousands of features.
Yeah.
And it has to be really good at automatic feature selection. And on top of all that, it's got to be able to handle these massive data sets. We're talking tens or even hundreds of thousands of training examples.
It's going to be fast, efficient, and be able to scale.
Exactly.
So some of the traditional approaches, like neural networks, they're out, right?
Yeah. Neural networks, they're powerful, but they're just not a good fit here.
Yeah.
I mean, the speed and the scalability demands of IML is just too much.
And I guess nearest neighbor algorithms, they fall short too, right?
Yeah, in this context, they just don't quite cut it.
So what did they land on? What did they find that actually worked?
Decision trees.
Decision trees, okay.
Or DTs, as they call them.
DTs, got it.
And they make a really strong argument for why these are the perfect candidate for IML.
Okay. So what makes them so special? What are the advantages there?
Well, first of all, they're really good at feature selection.
Yeah.
It's like built into their structure.
Uh-huh.
And another big plus is they can handle both discrete and continuous data,
Okay.
which is really important when you're dealing with image features.
So let's dive into the specific algorithms a little bit. What kind of DT algorithms are we talking about here?
So they focus on four main ones: center-weighted, or CW,
Okay.
center-weighted subsampled, CWSS.
DWSS.
Then you have mean split, MS.
Got it.
And finally, mean split subsampled, MSSS.
MSSS.
And each one has its own kind of strengths and weaknesses when it comes to accuracy and speed.
So there's some trade-offs there.
Exactly.
Okay, but that's all well and good, but how did these algorithms actually perform when a designer is using them?
Right. That's the real test.
That's the real world.
And, at the end of the day, what matters most is designer time.
How long does it actually take to create a functional classifier?
Exactly. And the authors were really thorough in their evaluation. They set up these 4 different test scenarios, each one kind of representing a different level of complexity for image classification.
Okay, such a...
So they had skin detection,
Okay.
paper card tracking,
Uh-huh.
robot card tracking,
Okay.
and laser tracking.
So they're really kind of trying to cover a wide range of problems there.
Exactly.
Got it. But to assess how well these algorithms actually do in a real-world scenario, they also define what they call a gold standard classifier for each of these scenarios.
Right.
So what exactly is that?
So for each task, they meticulously classified pixels until they reached what they considered the absolute best possible classification performance.
Okay.
And they did this on a set of test images for each of the tasks. So it's like having this expert level solution that you can compare against.
Got it. So you have this like benchmark. Okay. And then they had 10 test subjects.
Right.
And they split them into 2 groups.
Right.
And each group tried building classifiers using both CWSS and MSSS.
Exactly.
Okay. And so they looked at 3 main things, right?
Yes.
How long it took to create the classifier.
Right.
The number of classifying correct iterations.
Right.
And then the structure of the resulting decision tree.
Uh-huh.
So like how deep it was and how many nodes it had.
Exactly. Good stuff.
Okay, so what did they find? What were the results?
Well, one of the most interesting things was that MSSS, even though it was faster at training individual classifiers, it actually took a lot longer for the more challenging problems, things like the skin and the card tracking.
That's pretty surprising.
Yeah, it was interesting. It suggests that initial accuracy really can have a big impact on the whole design process.
So even though it's churning out these classifiers quickly, if they're not that accurate, you end up spending more time correcting them down the line. Interesting. But the users themselves actually reported that CWSS felt faster.
Yeah.
Especially for those more challenging problems.
Yeah, especially for those tough ones.
So it's not just about how quickly the algorithm is doing its thing. It's also about how efficient it feels to the person using it.
Exactly. Perceived speed and efficiency, those are really important factors.
Yeah.
Especially in IML.
Okay. So we've looked at the algorithms themselves. We've looked at how they perform. But we'll dive a little bit deeper into those findings and kind of see what they mean for the future of IML in the next part of our deep dive.
So yeah, picking up where we left off, those user evaluations really drive home a key point, in interactive design, where that user time is so valuable that machine learning algorithm, it has to be fast, but it also has to be accurate.
It can't just be one or the other.
Right, it's got to be both.
Got it.
And it looks like decision trees, especially those with, subsampling techniques like CWSS, they seem to strike that balance.
Yeah.
Leading to faster classifier creation and saving those designers precious time.
Makes sense. But let's shift gears a little bit here.
Okay.
The paper also spends some time talking about the specifics of feature selection in IML.
Right.
We're talking potentially thousands of features here.
Yeah.
And the algorithm needs to figure out which ones are actually important.
Yeah, and quickly.
Quickly, right?
And that's where decision trees really shine, their structure. It just naturally lends itself to feature selection.
Okay.
At each node in the tree, the algorithm is evaluating all those available features, and it picks the one that best splits the data.
Uh-huh.
And the features that don't really contribute to better classification accuracy, they basically get ignored.
So it's like this built-in filtering process that helps the algorithm zero in on the stuff that really matters.
Exactly. It's like a built-in filter.
Cool.
And what's really neat is that this feature selection, it all happens automatically. The designer doesn't have to manually step in and do anything, which is huge in IML, where speed and efficiency are so critical.
Right, so we're not just building classifiers faster. We're also making the process itself smarter, more automated.
Exactly.
I like it. But the paper also talks about overfitting.
Right.
Which is always a challenge in machine learning.
Yeah, for sure.
So how does that play out in IML?
Well, so overfitting, it happens when a model gets a little too good at learning the training data. It starts to memorize those specific examples instead of learning those generalizable patterns.
Right. It's like it's learned the answers to the test, but it doesn't actually understand the material.
Exactly. And in traditional machine learning, you might use techniques like cross-validation to combat that.
Right. You split the data into different sets for training and testing to make sure the model can actually handle new data.
Right.
But how do you deal with overfitting in IML, where you're constantly adding new training data and tweaking the classifier?
That's where the human in the loop comes in.
Okay.
The designer, by actually interacting with the system, acts as a safeguard against overfitting. They're giving feedback, they're correcting errors, essentially guiding the model towards a more generalized solution.
So it's this really cool back and forth between the human and the machine.
Yeah, it's a partnership.
I like it. No, the paper goes into a lot of detail about their evaluation methodology.
Yes, they do.
They use this approach with gold standard classifiers to see how CWSS and MSSS actually perform when designers are using them.
Right.
Can you walk us through that a little bit?
Sure. So remember they had those 4 test scenarios: skin detection, paper, card tracking, robot card tracking, and laser tracking.
Yeah.
Each one with a different level of difficulty for image classification.
So they had a good range of tasks to really put those algorithms through their paces.
Exactly. And for each scenario, they created what they call a gold standard classifier.
Okay.
And this was done by very, very carefully classifying pixels until they achieved what they considered like the best possible classification performance.
So it's like having this expert level solution to compare against.
Yes, exactly. It's the benchmark.
Got it. So how did they actually measure the performance of the classifiers created by those test subjects?
They kept it pretty simple. They used pixel agreement.
Okay.
So they compared the output from each subject's classifier to that gold standard classifier for the same task.
Uh-huh.
And if the subject's classifier agreed with the gold standard on more than 97.5% of the pixels, they called it a success.
Okay, so it's all about how closely the subject's classifier matches the expert's judgment.
Right.
But why 97.5%? Why not shoot for 100% agreement?
That's a great question, and it really highlights something important about IML and interactive design. Perfect accuracy isn't always the goal.
Interesting.
It's more about finding that sweet spot between accuracy and efficiency.
Right, because if you're spending hours and hours trying to get that last 0.5%,
Exactly, you're losing that efficiency.
it's not worth it.
Right, so
No.
they likely chose 97.5% because it's a practical target,
Okay.
recognizing that getting to perfect accuracy could take a lot of extra effort and time from the user.
It's a good reminder that in the real world, good enough is often more than enough.
Right.
So let's dive into those tables you mentioned earlier. Tables 1 and 2 show the average times and iterations it took for those test subjects to create their classifiers using CWSS and MSSS.
Yes.
What were some of the key takeaways there?
One of the big things that jumped out was that MSSS, even though it was faster at training individual classifiers, it actually led to longer overall design times for those harder tasks like skin and card tracking.
Again, seems counterintuitive.
Yeah, you'd think the faster algorithm would mean a faster design process,
Right.
but it turns out accuracy plays a huge role.
Makes sense.
Even if MSSS cranks out classifiers quickly, if they're less accurate, the designer has to spend more time fixing them.
Right, so they end up losing time in the long run.
Exactly.
Interesting. So even though CWSS might be slower at training, its higher accuracy could mean less time spent making corrections and therefore a faster overall design process.
Exactly, and this is backed up by the fact that users consistently said that CWSS felt faster, especially for those tougher tasks.
Right.
That subjective experience, it matches the data, really emphasizing how important that perceived speed is in IML.
It's interesting how user perception and those actual measurements line up.
Yeah.
It seems like they could really feel the difference in efficiency between those two algorithms.
Oh, absolutely. When you're designing these systems, you've got to think about the user experience.
Right.
Even if an algorithm is technically fast, if it feels slow or clunky to use, it's just not going to be effective.
Totally agree. Yeah. So that brings us to table 3, which looks at the structure of the decision trees themselves. What did CWSS and MSSS produce?
Right. So table 3 compares the average tree depth, the node count, and the average classification time. They call it ACT. For those classifiers created with both CWSS and MSS across all 4 of the test scenarios, and the results are pretty clear. CWSS consistently generated shallower trees with fewer nodes compared to MSSS.
So less complexity.
Yeah, meaning CWSS created more efficient classifiers.
So a smaller node count means a faster, more streamlined classification process.
Exactly, and that efficiency is reflected in that average classification time. CWSS consistently had lower ACT values, showing that its classifiers could make decisions faster.
Which is crucial for those real-time applications. Things like gesture recognition or object tracking,
Oh, absolutely.
where speed is everything.
Right, and that efficiency comes from the way CWS handles feature selection. It tends to build these more balanced decision trees compared to MSSS.
So it's not just about the accuracy, it's also about how well structured and efficient those classifiers are.
Exactly.
Okay, well, it seems like CWSS might be the winner here, especially when you're prioritizing designer time and classifier efficiency.
It's looking that way.
But I'm curious to hear your thoughts on the broader implications of IML. Where do you see this technology going in the future? We'll explore that and more in the final part of our deep dive. So we've talked a lot about the nuts and bolts of IML, how it works, those decision trees.
Right.
But the paper kind of hints at this bigger picture too.
Yeah.
This future where PUIs powered by IML
Right.
could be just seamlessly integrated into our lives.
Right.
It's a pretty exciting thought.
Yeah, it is. But they also point out that scalability is a big hurdle.
Yeah.
If we really want to make that vision a reality, the paper focuses mainly on image classification.
Right.
But these IML principles, they could apply to other kinds of sensory data too, like audio motions, even physiological signals.
So you could have systems that respond to your mood or your activity level or even like biofeedback.
Exactly. Imagine systems that can adapt to all sorts of inputs.
That's wild. That opens up so many possibilities for these truly personalized experiences.
Yeah, but scaling IML to handle all that data, that's a whole other challenge.
Right. It's not just about processing more information. It's about understanding how all those different inputs relate to each other.
Exactly. And that brings us to context awareness,
Okay.
which the authors really emphasize as key for IML.
So what do they mean by that?
So to build these really personalized and adaptive systems, they have to understand not just those direct inputs from the user, but also those subtle cues from the environment.
So like understanding the intent behind a user's actions, considering things like their surroundings or past interactions.
Right, or even their current goals. What are they trying to achieve?
Got it. So context awareness is really about getting the full picture.
It is. It's about understanding the why behind the what.
And that's how we get to those proactive systems.
Exactly. Systems that anticipate your needs and adapt to your changing situation.
Systems that just work.
Right.
Now, the authors also mentioned some real-world applications for IML beyond just PUIs.
Yeah.
Things like healthcare, education, even robotics.
Right. They highlight the potential for personalized medicine.
Okay.
Doctors could use IML to tailor treatment plans based on real-time data from wearables or other monitoring devices.
So it's like having a system that's constantly learning and adapting to each patient's specific needs.
Exactly. And it could alert doctors to potential problems before they even become serious.
That could be huge. And what about education?
So in education, IML could help create these adaptive learning systems that adjust to each student's individual learning style.
So every student gets a learning experience that's tailored to their strengths and weaknesses.
Right. Imagine a system that learns how a student learns best.
Yeah.
And then personalizes the pace, the content, even the teaching style.
That would be incredible. And robotics.
In robotics, IML could enable robots to learn from their interactions with people and their surroundings, making them better at handling those complex tasks.
So robots that can work alongside humans, understand our intentions, and provide assistance in a way that feels natural.
Exactly.
It's amazing to think about all the possibilities.
It is, but as with any powerful technology,
Yeah.
we need to be thoughtful about the ethical implications.
Absolutely. Transparency and accountability, those are critical, especially with systems that could have such a profound impact on our lives.
Couldn't agree more.
Well, this deep dive into IML has been fascinating.
It has.
It's really highlighted both the exciting possibilities and the responsibility that comes with this technology.
It's definitely given us a lot to think about.
As we wrap up, I think it's clear that IML has the potential to revolutionize the way we interact with technology.
Yeah.
And with each other. The authors have laid out a compelling vision.
They have.
And it's going to be really interesting to see how this field develops in the years to come.
I'm excited to see where it goes.
Thank you for joining us on this deep dive.
Thanks for having me.
We hope it sparked your curiosity about the future of IML and its role in shaping our world.